All right, we are at day 21 for Advent of Code. We're doing it in Rust. Let's get into it. Today's problem is called Dirac dice. I'm already scared. I know Dirac is a physicist. That's all I know. I'm not sure what the reference is here, but let's check it out. There's not much to do as you slowly descend to the bottom of the ocean. The submarine computer challenges you to a nice game of Dirac dice. This game consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces marked 1 through 10 clockwise. Each player's starting space is chosen randomly, your puzzle input. Player 1 goes first. Players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the results. Then, the player moves their pawn that many times forward around the track. That is, moving clockwise on spaces in order of increasing value, wrapping back around to 1 after 10. So, if a player is on space 7 and they roll 2, 2, and 1, they would move forward 5 times to spaces 8, 9, 10, 1, and finally stopping on 2. After each player moves, they increase their score by the value of the space their pawn stopped on. Player scores start at 0. So if the first player starts on space 7 and rolls a total of 5, they would stop on space 2 and add 2 to their score for a total score of 2. The game immediately ends as a win for any player whose score reaches at least 1,000. Since the first game is a practice game, the submarine opens a compartment labeled deterministic dice and a 100-sided die falls out. The die always rolls 1 first, then 2, then 3, and so on up to 100, after which it starts over at 1 again. Play using this die. For example, given these starting positions, player 1 starting position 4, player 2 starting position 8, this is how the game would go. Player 1 rolls 1 plus 2 plus 3 and moves to space 10 for a total score of 10. Player 2 rolls 4 plus 5 plus 6 and moves to space 3 for a total score of 3, and so on and so forth. Bunch of turns. Since player 1 has at least 1,000 points, player 1 wins and the game ends. At this point, the losing player has 745 points, and the die had been rolled a total of 993 times. So they add the losing player's score and the total number of times, or the total number of rolls of the dice. So that's 2 per turn. And they multiply the 2 together, rather. And that's probably the number that we're trying to answer. Play a practice game using the deterministic 100-sided die. The moment either player wins, what do you get if you multiply the score of the losing player times the number of times the die was rolled during the game? First, let's get our input. This particular problem, I think, is going to be really easy for part 1, and it's going to get crazy for part 2. Probably they're going to want us to get to score like 1 billion or something. All right, the dice that we're using, the die, again, I guess is a 100-sided die. It starts at 1, and then every turn it goes up to 100, then it wraps around again. Okay. Oh boy. I have a feeling this problem is about modular arithmetic, which I am not so confident in. So we'll see how it goes. Our input doesn't look particularly interesting this time around. There's really nothing to parse. You really just, player 1 just starts on 8, player 2 starts on 1. So I don't think there's any input parsing necessary for this problem. So let's even get rid of our input file. Okay. Player 1 starts on 8. Player 2 starts on 1. And we're just going to loop. Let's also keep track of their scores. We have P1 as their position 1 and S1 as in score 1. And then we have P2 and S2. Okay, so let's also keep a counter of the number of rolls. Okay. And then we need to know what the previous die roll was. Or let's call it the next roll. The next roll is 1. So player 1's position is equal to P1 plus next roll. And then this is going to wrap around, right? So to do a wraparound, I believe what we need to do is this is actually going to be modulo 10 arithmetic. But the numbers start at 1 rather than starting at 0, which because a modulo 10 space goes from 0 to 9, right? So if we want something that goes from 1 to 10, what we can do is we can subtract 1 from this original value, do this modulo 10, and then add that 1 back on, right? So let's say that we're at position 8 and we roll 3. That's going to put us at position 11, which should be back to position 1, right? Now, if we just do position 1 like 8 plus 3 and then do that modulo 10, we'll actually get the value 2, which is not correct. So, but what we can do is we'll do 8 plus 3, which is 11, subtract 1, which is 10. 10 modulo 10 is 0. But what that 0 means is we really want to be on the 0 index value that is in our set, and our set goes from 1 to 10, so we'll just add 1 back on to get us back into that space, right? We'll add 1 to next roll. Roll plus 1. And we need to do a similar wraparound for the dice here, right? Because it's from 1 to 100. So it's plus 1 minus 1 modulo 100 plus 1. So because it's plus 1 minus 1 here, it's a little bit pedantic that I'm typing this all out. It might be worth me just actually making a function here. Mod starting 1. It's probably going to be just an I32. You know what? I think I'm not going to write this function because I don't even know what to call it. And anytime you sort of like are trying to decide how to name something, it's better just to give it do something really, really ambiguous. And I don't think we're going to be doing this math enough to really warrant a separate function. So if P1 is greater than or equal to 1,000, then we're done, right? We can break out of the loop. And then now we're just going to do the same thing with P2. So we'll just repeat this. It's all P2. And, oh, we need to adjust the score, right? So actually, we'll say is the score equal to the roll or the position that they land on? I think it's the position that they land on, right? So if the player moves to space 10, they add 10 to their score. If they move to space 3, they add 3. Okay. So what we're going to say is that score 1 plus equals position 1. And score 2 plus equals position 2. If either of them hit 1,000, we're going to stop the loop. And finally, we're going to print the number of rolls. So we actually need to increment the number of rolls. Do the number of rolls times the minimum of P1 and P2. No, score 1 and score 2. Oh, you know what I'm doing? this should be the score here. It's running infinitely. Okay, so 197,109. Answer's too low. Shoot. Okay, so let's actually just try to run the example that they're doing here. Oh, I see. What I'm missing here is that they actually roll the dice 3 times. Okay, so is there a convenient way to do this mathematically? Because I could just copy and paste this a bunch of times, right? The other thing we could do is just make a lookup table, right? We could just figure out what each roll is going to do, or each roll of 3 dice, and figure out how that's going to advance your position. And maybe that will be a little bit easier. So how will that look? How many total turns are there? If you have 1, 2, 3, 4, 5, 6, 7, 8, 9, that's going to be 1 roll. That's going to be the next person's turn. This is going to be the next person's turn. 10.11.12. Let me put a dot in between the roll values. Dot, 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 dot. All right, and that's going to go all the way to, I believe, 97, 98, 99, and then, or actually it's going to go all the way to 97, 98, 99, and then it'll go to 98, 99, 100. No, it'll go to 100, 1, 2. And that's going to wrap around. Then it's going to go 2, 3, 4, 5, 6, 7. And it will wrap around what's the last number that we're going to get here before we get to 100? Will it be I think it's 96, 97, 98. And then it's 99, 100.1. Let me actually put some new lines to show where it wraps around. And it'll be 2. Wait, I made a mistake here. This is actually 3, 4, 5, 6, 7, 8, dot, dot, dot. That's why the numbers were looking a little bit weird to me. So I think basically if you subtract 2 from the last number, it should be divisible by 3, right? And that's true. Is 95 divisible by 3? I don't think it is. So I think I miscalculated that. Oh, never mind. You subtract 2 from the last, and 96 is divisible by 3. Great. And then this is going to be 2, 3, 4, 5, 6, 7, all the way to, and this should end up with 98, 99, 100, and then wrap around back to the beginning. And in this one, if you subtract 1, it should be divisible by 3, and that's certainly true there. Okay, so what I want to do is just make a lookup table that has, what is it? 33 times 3, 99 elements in it. because there are 99 different combinations here, right? There's 33 here, 33 here, 33 here. So for let mute, it's really like roll sums. So it's like sums, which is a vector of I32s. Let's make that a new vector. And we are going to just go 99 times, I believe. The next is going to be 1. And then for 0 90 to 99, we're just going to add, we're going to say that like sums.push next plus 1 plus next plus 2. Although this may have a wraparound, so we need to keep track of that. So we're going to say let A equals next, let B equals next plus 1 minus 1 modulo 100, because we're wrapping around, plus 1. And then C is going to be the same thing. Only it's going to look like that. And then we're going to push in our sums. A plus B plus C. And we're just going to do that 99 times, although we need to advance next now, right? So next is equal to next plus 3 minus 1 modulo 100 plus 1. And then I want to know, basically my first value in this array should be, or in this vector, should be 1 plus 2 plus 3, which is 6. And the last one should be 98 plus 99 plus 100, which is what? 300 minus 3, which is 297. So let's go ahead and just print that out. Sums. Okay, starts with 6, ends with 288. So I didn't go enough times. I think maybe 99 is the wrong number of times. Maybe what we can say is if next equals 98, then we're done. Because we know that 98 is going to be the last one of these unique things before it comes back around. So it looks like we're terminating. I think we might be 1 short. Next should actually be 1. This is when we know we've wrapped it fully around. I'm much more comfortable with this particular answer. But if next is 1, that's right, I got to adjust the while loop. 297. Okay, that is a lot better. Okay. Okay, so what did we even just do there? We just created like an array of sums, and I think what this just means is each time a player takes their turn, we know how many spaces ahead they should advance just by looking at this, right? And in fact, if we wanted to avoid modular arithmetic entirely, what we could do is actually just make a lookup table that pairs every position with every possible move forward, or rather every index in this move forward, to get us essentially just a lookup table of where they're going to end up, right? So why don't we try that? So for pause in 1 to 10, right? And then for move in sums.iter, we can actually just call this rolls. And oh, move is a keyword in I don't know if move is a keyword in Rust. I think it's when you write closures, and you can basically move values into the closure. So if I can't use the word move, shoot, for roll. And really, this is actually I want the index of the roll. So steps, maybe we'll just call it. We are going to say let outcomes is a hash map of a position, which is an I32, and a usize, which is basically which index, which roll, which like deterministic roll set are we on? Like which roll of 3 dice are we on, or which index in this vector are we on? Let's create a new hash map. It's going to complain because I need to import. Oh, it's actually imported already. I just need to know what the outcome is. And the outcome is a position that it lands on, which is I32. We might end up using usize for this, but I don't really know yet. Okay, so what we can determine here is we'll say that your position, let next pause, is equal to your current position plus the number of steps. And remember, we got to do this like modulo thing here. This is like the one place where this -1 matters. Modulo 10. And then we are going to add 1, right? And then outcomes, we're going to insert in outcomes. Our key is going to be the tuple of our position and which essential like deterministic roll of 3 dice we're on. And then we're going to put next pause in there. Okay. So now what we can do, now that we've sort of done all of that business, is we can basically say let mute n rolls is the number of rolls, and that's going to start at 0. Actually, you know what? We're going to just basically have all of these things. We're going to still have those. And our next roll is going to be actually 0. It's going to be the index into our array of rolls. Okay, so we're just going to say that P1 is going to equal, so let next P1 is going to equal our outcomes. We're going to just fetch from outcomes. And we're going to do P1, the player one's current position, and the roll index that we're currently on, right? P1 is going to equal next P1, and then player 1's score, we're just going to add next P1. And then we're going to increment next roll. Next roll is going to add, we're going to add 1 to that. And we can do this modulo the number of total rolls that we have. Right? Because we're just traveling through this vertex, this vector. And we just want to make sure that we are starting back at the beginning once we're there. Why are you complaining about length here? Rolls is I32. Did I overwrite something? I did. Num rolls. We'll do that. And then we're just going to repeat this for player 2. So basically, every place that we see the number 1 here, except in our math, it's going to be a 2. Okay, this is a fair amount of code. I hope I didn't make a silly mistake in here, but let's give it a shot. Am I still debug printing anywhere? I don't think so. Oh, and then this is num rolls. Down here. We're not using this anymore. We never were using it in the first place. Very aggressive auto import. 172,000. Wasn't that less than what we got before? I somehow think it is. Yeah, it's too low. Okay, so what? This is a lot of galaxy brain kind of thinking here. I want to make sure that I did this correctly. So we can try using the sample input here. Player 1's position is 4. Player 2's position is 8. After many turns, so they played 993 turns. So let's go ahead and actually just print everything out down here. So we're going to print the number of rolls, S1 and S2. So using the sample input, what are we getting here? Only 331 rolls. Are we adding too much? The way that we get to this point is we're adding too much score. So what we could do is, what is our outcome? Let's print here. P1 move. The roll is some value. The position is some value. The roll is some value. The new position is some value. And the score is some value, right? So what we are going to do here, actually we need to remember what P1 previously was. So let prove P1 just for debugging. Actually, let's even put debug in the name is P1. Let's do prev P1 debug. The roll is rolls of next roll. The new position is P1 and the score is S1. Let's do the same thing for player 2 down here. And we are going to store the previous position of player 2. Okay, so player 1's position is 4. Starting position is 4. The roll is 6. The new position is 10. The score is 10. Okay, so far so good. Player 2 rolls 4 plus 5 plus 6. 4 plus 5 plus 6 is 15. The new position is 3 for a total score of 3. Okay. Player 1 rolls 7 plus 8 plus 9. What is 7 plus 8 plus 9? It is 15 plus 9, which is 24. The new position is 4. Let's try and split these so we can read it more easily. New position is 4, the score 14. I will make my life easier if I print the right player number here. So let's try that one more time. Player 1 rolls, it gets 14. So it's 9, 20, 16, 26, 22. So that actually looks pretty good. What I'm confused by is that at some point we add like a huge amount. Because our number of rolls is too low. They rolled in the sample, they rolled 993 times. I only rolled 331 times. Although player 2 does have 745. Am I? Oh, you know what it is? The number of rolls I need to add 3 to every single time, right? Because these represent 3 rolls. That's the bug. 993. Okay, fantastic. Okay, so I think I got it right this time around. So now, if we just restore this, this is just num rolls times S1, S2. The minimum between S1 and S2. It keeps adding this num here, and I think a lot of my debug printing can go away at this point. Let me just make sure I got the right answer. 739,785. All right, so let's go back to our original values, which I believe are 8 and 1. Yes. We'll run that. That's 518,000. That is significantly larger than we had before, and we got that correct. Cool. Okay, so before I continue, I'm going to go ahead and get rid of some of my debugging code here. Run that, make sure it compiles. Okay, and we're going to go ahead and just shove this into Git. Okay, let's go ahead and move on to part B. I'm going to make a copy of that directory. Make day 21B, it compiles, we got the same answer. Okay, we are looking good. Now let's take a look at the instructions. Now that you've warmed up, it's time to play the real game. Oh boy. A second compartment opens, this time labeled Dirac dice. Out of it falls a single 3-sided die. As you experiment with the die, you feel strange. An informational brochure in the compartment complains that this is a quantum die. When you roll it, the universe splits into multiple copies, one copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies, one where the outcome of the roll was 1, one where it was 2, and one where it was 3. The game is played the same as before, although to prevent things from getting too far out of hand, the game now ends when either player's score reaches at least 21. Using the same starting positions as the example above, player 1 wins in this many universes, while player 2 merely wins in this many universes. Using your given starting positions, determine every possible outcome. Find the player that wins in more universes, and how many universes does that player win? Wow. Okay, so we're clearly not going to be able to actually simulate every single possibility, right? Like, I don't even think if you just wrote a for loop to count a number this high, your computer would be able to do, our computers would be able to do that. So we're probably going to have to come up with some way of summarizing possible branches of the universe and then just doing addition. All right, so there's not a lot of our original solution that can be recovered. Because this is like a very straightforward and literal way of implementing the solution, and we want to do something a little bit more clever. This is going to take me a while to figure out, I think. So how do we count universes in the first place? A universe is just one particular outcome of the game. And each time we roll the die, we actually split into 3 universes. This actually may be a good place for me to try to draw this out. So I'm going to grab my iPad here and see if I can't sketch out some of the thinking. I think this is one day where I definitely wish I had a second brain to kind of bounce ideas off of. And maybe if I get super stumped by it, I might have to take a break, and then maybe since we're streaming tomorrow night with Dom, maybe I can sort of Shanghai some of that stream into trying to solve this particular problem. Assuming that day 22's problem, which I'll also try to work on tomorrow, isn't also super difficult. I'm sure there's a solution that, or there's some people who are working on this where the solution just came to mind immediately for these folks, but I am not one of those people. Certainly not. I'm gonna pause for a second here. I'll be right back.
5 minutes later.
Okay, we are back for Advent of Code Day 20, Part 2. So there are like different levels of cluelessness that at least I feel when I'm working on an Advent of Code problem. Sometimes you look at a problem and you kind of already know how you're going to tackle it. Sometimes you look at a problem and you don't really have a strong idea of what the implementation will look like, but you have a hunch that you can follow. I'd say there's probably like strong hunches and weak hunches. And then there's ones where you just are like totally clueless. And right now for this one, I am in that last category. And the only thing we can do in that situation is just kind of like try to visualize the problem into something a little bit more basic to see if we can find something to take advantage of. So the nature of the game is this. We're essentially playing a game where 2 players are on a board with a map or like a path, and the path loops around. You roll some dice, and you move ahead on that path, and whatever position on that path you land on, you add to your score. Pretty simple. It's all a matter of, it's basically a 100% luck game. There's no skill involved for those players. The way we roll dice is that we have a dice that we can roll 3 times, and we add up the total, and that's how much you move forward. And in this case, you're in part 2, we're really just trying to see which player hits 21 or greater first for their score. Now the rub here is that essentially each time a player rolls the dice, so that this is actually 3 times for each player's turn, the universe splits into 3. 1 universe for every single possibility of the dice value. And then that happens every single time. We're basically just trying to count how many universes, given this sort of like magical quantum die, that the first player will win versus the second. And all we start with is the behavior of this dice and the positions where player 1 and player 2 begin, which are common, right? So to sketch that out, let's say this is turn number 1. Player 1 goes first, and on their first dice roll, the universe splits into 3. 1, 2, and 3. And for each, so this is P1. Maybe the way that I'll do this is P1 roll 1. Could be 1, 2, or 3. And then each one of these splits into 3 outcomes. P1 roll 2. This is 1, 2, and 3. And then each one of these splits into 3. And that's P1 roll 3. And now we're done, at least when we've gotten to this level, we're done with player 1's part of the turn. We add up the sum of what they got, and then we see, have they exceeded 21 yet? And if they have, then we stop the game and they've won that. They won that particular leaf of the tree. Otherwise, we go to player 2's turn, and player 2's tree looks exactly like player 1's tree, right? Only it's kind of like under here. So next we go, basically we have 3 outcomes here, and this is player 2 roll 1 with a 1, a 2, and a 3, and so on and so forth, right? I do wonder here, just looking at the fact that these are trees, if there's a recursive relationship. So for any given player's turn, we could basically say, well, how many universes, like if player 1's going to win, it's basically like, well, how many different dice roll possibilities are there just for player 1? Well, it's essentially going to be how many leaves do we have at this tree, right? That's the number of dice roll outcomes per turn per player. And that's going to look like, well, we've got 3 possibilities at the layer of roll 3, 3 at the layer of roll 2, and 3 at the layer of roll 1. So that's 3 times 3 times 3. So there's 27 possible outcomes, right? Now, they don't all actually share the same value. The actual number of unique values is going to be way less than that, right? And we can kind of just write them all out, right? Like in the case, like if we were just rolling it twice, we get 2 here, 3 here, 4 here, 3 here, 4 here, 5 here, 4 here, 5 here, 6 here. That's just for 2 rolls of the dice. And so 2, 3, 3, 4, 5, 6. This kind of has a nice diagonal symmetry to it. If we roll the dice one more time, we basically have these additional outcomes. So it'd be like 3, 4, 4, 5, 5, 5, 6, 6, 7. And this would just be one more than that, which is 4, 5, 5, 6, 6, 6, 7, 7, 8. And then if we rolled 3 on the last roll, we just have one more than that second row. So that'd be 5, 6, 6, 7, 7, 7, 8, 8, 9. So this box over here is the number of this is basically the possibility chart, or essentially it's the histogram, or it's the distribution of dice roll totals for anybody's given turn. This kind of analysis is how people figure out, like, okay, well, what is the best property in Monopoly in terms of people landing on it the most. I believe it's Illinois Avenue. I think New York is also pretty good. I know the reds and oranges are in general pretty good in Monopoly. And the reason why they can do the analysis is they essentially just look at the roll of 2 six-sided dice. What are the most common totals for 2 six-sided dice? Which I think is just 7 is the most common number, right? So 7 is not only lucky with 2 six-sided dice, it's also the most common. So it's nice that they made the luckiest number the most common one as well. Still lose though. Don't gamble. Is what I'm saying. Don't gamble. Don't buy NFTs. Is the lesson for this advent of code. So I wrote all this out. I don't know where this is getting me in this particular problem. Because we want to just like count universes, right? Okay. I'm drawing a blank right now, so if I'm silent, I'm just basically trying to chew on my thoughts. If there's anybody lurking in chat, feel free to pipe in and give me a hint at this point. Not a spoiler, but just a little hint. Otherwise, I'm just gonna sort of like be making very pensive faces as I stare at my tablet here, trying to figure out what insights we can get. This would definitely be like a super scary job interview problem, right? Like, can you imagine being thrown this like kind of curveball brain teaser in the middle of a job interview? Which I feel like maybe 20 years ago, that kind of thing would have been like super kosher or just accepted. Possibly if you were to like interview at like a Google or something like that, they may still want to throw one of these bad boys at you. And certainly this problem is like past my limit of being able to solve gracefully while someone is watching me, let alone a situation where someone's watching me and there are like stakes, like a job offer involved. But that's okay. There's nobody offering me a job here. We're just doing this for fun. So even with that, like that amount of pressure lifted off my shoulders, can I still figure this out? I had this idea of just trying to figure out recursively where the number of universes where you win at 21 are basically the number of universes where you roll, one of these numbers in this table in the upper right here. And that still might be relevant, but like even if we did establish like a recursion relation, we could do recursion maybe with caching, and that would help. but I don't know. This almost felt like a dynamic programming problem to me, where we basically do the counting from the bottom up rather than from the top down. I don't know if that's meaningful to anybody, but like for me, framing problems in terms of dynamic programming was never natural. I always just had to come up with a recursion relation, and I found that recursion with memoization was always like the easiest thing for me to do. But it doesn't matter if like how you're doing your caching. If you can't come up with a recursion relation in the first place, you haven't really solved the problem, or you haven't even begun to solve the problem yet. So how do you get to 21 or greater, right? You get to 21 or greater you get to greater than equal to 21 if you previously had 18 and you roll a 3, or if you had 17 and you rolled you rolled a 3 or above, right? 17 if you rolled a 4 or above, 16 if you rolled a 5 or above, 15 if you rolled a 6 or above, and these rolls that I'm talking about are totals. 14 if you rolled a 7 plus, 13 if you rolled an 8 plus, and then 9 is the maximum possible total, right? 9, right? There's no plus at that point. Actually, this isn't even that simplistic, right? Because I'm just adding I'm actually misinterpreting the problem entirely, right? It's really more your score that you add is the position that you land on, right? So let me erase all this. And you can either get a 1, you can get basically any value from 1 to 10. So how do you get a 21 or over? If your previous score was 20, any roll will get you to 21, right? And then if your previous score was 19, if you land on 2 or above, and then if it's 18, if you land on 3 or above, and then so on and so forth, all the way down to 11, where you have to land on space 10. So what's tricky about this is even if I establish this recursion relation where I can just basically count the number of possibilities in this tree of possibilities where you do actually get to 21 or greater, this doesn't account for the other player, right? Because in some of those universes, the other player got to 21 first, and you are basically not able to proceed. All right, I'm going to think about this for like another 10 minutes. And if it's not coming to me, then essentially I'm going to just like throw up the white flag just for tonight. I'm going to say I'm blocked. My kind of like unconscious brain will stew on it for a little while, maybe even overnight. And if I still don't have a great answer for it, I'm going to put this in front of Dominic, and if there's time tomorrow during tomorrow's game dev stream, we can try to solve this together. But I'm still gonna. I'm not ready to throw up the white flag today just yet. I'm gonna give this another 10 minutes. But it is important to know in any kind of activity, but in particular software engineering, when you are blocked. It is important to know when you are blocked, and when either to ask for help or when to just like step away, take a break, eat a meal, and then come back to the problem later. But I'm not there yet. I'm 10 minutes away. Okay. So if we were actually trying to enumerate all of these, can we build it up from the bottom, right? Like, okay, let's just try and solve. I sort of like stopped myself short where I was like, well, even if I can figure out how many universes will get player 1 to 21 or over, like how many different ways you can get to that. Let's just count those assuming player 2 doesn't exist. Right? Maybe at least solving that problem will push us ahead a little bit. Assuming player 2 doesn't exist, we've got the table over here that we've sort of written out, and each one of these numbers has its own table, right? This is where the recursion relation comes up. And I'm going to use a different color than red. That's a little bit easier to read. So greater than or equal to 20. So it's however many times you get to 19, and you roll any outcome. However many times you go to 18, and you roll a 2 or above. How many times do you get to 17? You roll 3 or above, all the way down to 10, and you roll arriving on a 10. And I'm kind of wondering if there's any overlap between what we calculate here and what we calculate here. Is there any overlap? Well, the overlap, for example, if we just want to compare the 18 case, this 18 and this 18. For this top one, right, for this top thing, if you're at 18, how do you end up on? Oh, you know what? And then here's the even trickier thing is like I'm just assuming that like you're naively adding the score onto that, but it also depends on what position you happen to land on. Right. So it's not just that it's 18. It's like, well, how many times are you on 18? And then do you have a score of 18? And then you're on position 1 and get a 3 or above. Right? So it's actually kind of a multi-layered thing, because the way we increment the score isn't just by rolling the dice. We have to roll the dice, move the player forward around this circle, and then add the index of the position that they're on. Man. Like, okay, what if I just like reframe the problem in a similar way that I reframed it before? Let's say player 2 isn't playing, and you just want to determine how many different ways can player 1 get to 21 or greater. Can you even count those number of possibilities? Well, we could just write it recursively. Let me just write that program and then see how far along that gets. And even just by writing the program, I think it'll help us like at least exercise our processing of this. But you know, before I talked about like different levels of cluelessness or different levels of helplessness when doing these problems, I don't know if I'm any closer just by doing this, but I'm going to write it out. So again, the sort of smaller problem I'm trying to solve is like how many different ways can player 1 arrive at 21 or greater? And that's definitely not going to be the same thing as the number. It's going to be greater than the number of it's going to be greater than this number, right? Because player 1 might reach 21 after player 2, which means we need to subtract off those times that player 2 gets there first. But it is an easier problem, but it's also equally, or it's basically roughly in the same level of infinity as the actual problem is. So at least maybe like kind of like banging it out will at least get the juices flowing a little bit. So again, the question is how many ways can player 1 get to 21 or greater? And we could just write a simple recursion relation, just saying fn, let's see, count ways to 21, and we have the current position, which is an I32, current score, just call it score. And that's it, right? And then it's basically some vast number, I64. In fact, let's just use all I64s just because it's a little bit easier to think about, okay? So if the score is greater than or equal to 21, we're done. We just return 1, right? There's only one way that you can get to greater than or equal to 21 at this point, is just by like not rolling the dice at all. Otherwise, we want to add up 3 different dice rolls, right? So our 3 different dice rolls, that addition here is essentially just this one here. So maybe we can actually even just copy that table down. That table looks like this. Three, 4, 4, 5, 5, 5. I'm going to reduce this down to sums later. Like how many times does each number occur? 4, 5, 5, 6, 6, 6. Rock and roll. 7, 7, 8. 5, 6, 6, 7, 7, 7, 8, 8, 9. If you squint, this has a kind of cool, again, diagonal sort of, I don't know, basically it'd be like each number appears twice diagonally here. So what the histogram of this, which maps values to frequencies, 3 appears once, 4 appears 3 times, 5 appears a lot. Let's see, 3 plus 2 plus 1. 3 plus 2 plus 1 is 6. Can't even do basic arithmetic right now. My brain is so jumbled. 6 is also, it's actually 3 plus 2 plus 2. So that is 7. 7 is 3 plus 2 plus 1 is 6. 8 is 3. And 9 is 1. And yeah, we'd expect basically this kind of pyramid looking kind of thing here. So what we're going to do is we need to and this is based on the current position, right? And these are the dice rolls. So we actually want to go backwards from current position, right? We're going to go backwards either 3 units, 4 units, 5 units, 6 units, 7 units, 8 units, or 9 units, right? So we want to do some backwards modular arithmetic. And the way that I will do that is we can do cur pos plus 10 minus the position that we're going to. And again, if we move current position 10 spaces forward, we're basically back at current position. We're going to subtract whatever our dice roll total is. Roll total that doesn't exist yet. And we're going to do this minus 1 modulo 10 plus 1 business to get the previous position, right? So that's the previous, let prev pos equals this. And we're just going to do count ways to 21. Of prev pos. And the score that we're trying to get is score minus the current position, right? Because when you were on the previous position, in order to get to this current position, you rolled some number, you rolled this roll total, and then added the current position onto that, right? And we're going to do this prev position and roll total, or rather roll total is going to be one of these 3 through 9, and then we're going to multiply this by the roll frequency. And then we're going to add these all up for every pair of roll total and roll frequency, right? So we could actually do a little like hash map. So let histogram equals the vector. And the vector is what? 3, 1, 4, 3, 5, 6, 6, 7, 7, 6, 8, 3, and 9, 1. So that's our histogram. And so what we're going to do here is we're going to iterate over the histogram. I guess technically we could do a fold, right? We could do a histogram dot fold, and we're going to start at 0 ways, and then what we're going to get is a roll total and a roll frequency. And it is going to be this expression here, let previous position equals this. And we actually need to receive the accumulator when we do a fold. So this is our running total, right? So we're going to add the running total to, so I don't think it can fold without an iterator. Yeah, there we go. Okay, why is it complaining about 0 here? Is it because I'm not returning mismatch types? Did I add a semicolon over here? I did, yes. Okay. Okay, still complaining about the 0. I think I just have a little bug here, which will be easier to resolve if I got rid of some of this noise. Okay, so that actually I think works. Now, I think this is going to be like super massive, and essentially what we'll want to do is like cache these. Right? We'll want to cache these outcomes. But essentially what we're going to do is we have like the running total based on what, you know, if I previously rolled a 3, or if I previously rolled a 3, that's only going to happen like once out of all the 27 possible universes that we have. Actually, one good exercise is do these frequencies add up to 27? 1 plus 3 is 4, 4 plus 6 is 10, 10 plus 7 is 17, 17 plus 6 is 23, 23 plus 3 is 26, 26 plus 1 is 27. Great, so they do. And we're going to just like, essentially because we can get to that particular dice roll, or that roll total multiple times, that's why we're multiplying by the frequency. And then we want to do this in a way that is cached. Okay. Now here's the thing with caching. In Rust, this is I think an area where Rust does not do so well, because like I basically just want a global cache somewhere, a global like lookup table that basically like I can store these answers in. And global variables Rust isn't so amazing at. So what I can do is actually just make this a structure. Let's just call it the solver. And the cache is a hash map of arguments to count ways to 21. So it's an I64, mapping to a number of ways, right? Okay, so now what we can do is we can do an implementation for solver. We'll write some methods on it. And what we can do is we'll just call it count ways to 21. In fact, we can just include this function in here. But what it'll do is it'll actually try to do, actually 21 is not what we want. We want current, like ways to score. So score here is actually current score. And want score is also an I64. And actually, these can all be really small. And so count ways to, it's not count ways to score. Okay, count ways to score. It's no longer count ways to 21. And what score are we going to pass recursively? Is it just want score minus current position? So let's say we were previously at position, like we landed on position 2. We had whatever score we had before. But because we landed at position 2, yeah, I think the subtraction is correct. Like, what we care about is how many different ways we get to score 19 if we were arriving on position 2 previously, right? So what we need to add here, though, is a mutable reference to self, because we're going to be updating a cache. And this is current score, right? And this formatting is very wonky. I would much prefer if we just split this into multiple lines. I don't think that the formatter will let me do it, but let's see. Yeah. Let ways to score so let's say the recursive result is this, and we'll just plug this in here. Normally you want a tail recursive solution, but I'm not going to worry about that for now. Although it might matter here, just given how slow this is going to end up being. Okay, so if current score is greater than or equal to want score, we can just return that. Otherwise, so this cache is actually going to be, let's actually turn these I64s into just like, it's going to be U32s. Really, they just need to, this position needs to go from 1 to 10. I'm going to make these I32s. I don't want to make them too big. Although I think on a 64-bit machine, it doesn't matter. I32, I64, or I32. If let sum num is equal to cache.get of our current position, our current score, our want score, then we just return num. Self.cache.get. We need to dereference. And this needs to be a reference, I believe. Yes. Okay, so the reason why it's good that we stored this. Actually, let's do this multiplication here. Let's call this the child result. Oh no. What we had there was fine. It was fine. What I want is this result here, and I'm going to store the result into the cache. Cache.insert, cache.add, or self.cache. Insert, and it's going to be this sucker here. It's our hash key. The value is the result. And then we finally return the result. Okay, so I'm gonna, let's see. So all this kind of like wraparound math is being taken care of here. And we don't have to worry about wraparound math for the deterministic die anymore. That was the challenge for the first part of the problem. But that's not a concern for us right now. So let us try and run this. Let's say that player let P1's position, and let's use actually the example in, let's use the example here. Player 1 starts where? Player 1 starts 4. Now, when we run this, we're going to hope that player 1's, the total that we get is actually much higher than this. P1 pause is 4. And then let's just println count. Oh, we need to actually create this counter. Let mute solver equals solver, whose cache is just a hash map. And let's do solver.count ways to score. Current position is P1 pause. Current score is 0. And the want score is 21 or greater. Now, if this runs to completion at all, I'll be a bit surprised, but it'll get us a little bit further along into our... Oh, I don't think that actually compiled. Am I in the wrong file? I am in the wrong file. I think I'm in 21A again, which is a good thing that I put things in get, because I don't want to clobber my old solution. So let's check out what's going on here in source control, get status. Let's get check out all of day 21A. Don't want that to be modified, but 21B is still chugging along. Kind of a rookie move, but let's go ahead and make day 21B one more time, and let's see what happens. Thread main is, oh, okay, so we have a stack overflow. And I think that is because we are not able to make this tail recursive, right? In fact, we can actually just print out these 3 arguments. And we can actually just sort of see how this is progressing along. And at some point, it's going to overflow, right? Oh, we're getting negative numbers. That is interesting. So how do we avoid negative numbers? If current score minus current pause is less than 1, we just return a cum. Or if want score I think 0 should be a possibility, right? So I think what it is if either of these are negative, we just return a cum. Otherwise, we do this. Oh, that's interesting. We return 0. It only happened once. Current score is greater than or equal to want score. I think this recursion is wrong. Or what it is count ways to score. We actually need to start from multiple starting points here, right? So how do we get to 21 if our current score is 21? Only one way of doing it. That doesn't seem right either. Okay, so clearly the recursion for this is also going to take a little bit of thinking. I think this actually is not a bad stopping point, because I think what I can do is, like, this has got some potential to it. It's a very complicated recursive relationship. We're not even taking into account the complexity of number of universes where the second player wins. But this feels like slightly warm. I'm no longer like desperately clueless. I'm just like mostly clueless now. So what I can do is I can just pick this up next programming session, and when I stuff this on the YouTube, we can just stitch the two sessions together. So we'll call this a stopping point. It's dinner time over here on the West Coast, and we'll pick it up some other time. All right, hopefully soon.
5 minutes later.
Okay, we are back for Advent of Code Day 21 in Rust. I took a little bit of time off when I took a little bit of time off after trying to solve the problem the first time, had some dinner, had some dessert, and then I had kind of like a brainstorm, and I think I figured out how to do it, which just goes to show, I think, that taking a little bit of time away from programming really, really does help. So we're going to pick it right back off where from where I last left off, which I think is maybe a more confusing angle than I needed the problem to be. So the way I had it set up was I had some intuition that we were going to be doing a recursive solution. And the original way that I wanted to do it was that I would basically write a function that would tell me how many ways I could achieve a particular score given a current score and current position. And I think I want sort of something that's a little bit similar to this, but I think we can model the scenario in the problem more directly with a recursive function. And the way that I think we can do this, we still want a cache of some kind, because the cache is going to basically give us memoization, right? And what memoization is something that will allow us to accelerate a recursive algorithm so that it's not just taking forever. But really, I think what we can do is just make the recursive function literally model one step or one player's turn in this problem. So rather than call it count ways to score, or maybe what we're just going to do is just have a function that just says count wins, and what we really mean by count wins is just the number of universes where player 1 wins and the number of universes where player 2 wins, given some certain starting conditions. Okay, and that's really the crux of it. So the return value of this function is basically going to be two 64-bit numbers. The first one indicating how many times player 1 would win given those starting conditions, and the second number is just the number of times that player 2 would win given those starting conditions. So now we just need to talk about what those starting conditions are, and there really aren't that many, right? First of all, we have player 1's position, and that can just be an I32. I use I32 if I just don't care really about the type. And then we have player 1's score, which is also an I32. Honestly, the position is a number from 1 to 10. The score is a number from 0 to 21. So really, these can be all like U8s if we wanted it to be. Let's actually just do that. Then we have player 2's position, which is also U8, and player 2's score, which is a U8. And then what we have is one final thing that describes the situation we're in, which is basically whose turn is it, right? And I'm just going to call this player 1 turn and make it a Boolean. Since we only have 2 players, I'm not going to bother making this like an enum or anything like that. It's just like this is true if it's player 1's turn, and it's false if it's player 2's turn. Or sorry, it's false if it's player 2's turn. Now, these arguments here are going to make up our cache key. So our previous cache when we were trying this problem before was just a bunch of 32-bit numbers. Here we're just going to copy these types, make a tuple. It's like a 5-tuple, right? There's 5 elements here. That's going to be our key. And then what we're caching is the result, the return value of this count wins function. And that's a tuple of two 64-bit numbers. I'll update the cache once we have to worry about it. I'm going to go ahead and chuck all of this stuff. We don't need it. I'm getting rid of it. Okay, so what we can do is just like given a certain starting scenario, like how many times, how many scenario within this given starting scenario, if we play out all the different quantum unfoldings of this situation. How many times will player 1 win and how many times will player 2 win? Well, I think the first thing we can do is we can just say if player 1's score is greater than or equal to 21, what we're going to return is just the tuple 1, 0. Because given the starting scenario, there's really only one universe that is possible. It's player 1 winning and player 2 not winning at all. Similarly, we have player 2 score. If player 2 score is greater than or equal to 21, because remember, player 1 takes precedence, then we're just going to return sort of the inverse of that tuple, 0, 1. Otherwise, we actually have to count. Okay, so I wish I didn't get rid of the histogram here, but we basically have to count the number of times, given this starting scenario, that player 1 will win if player 1 rolls a 3. And then the number of times in sort of the future quantum unfolding that player 1 will win if player 1 rolls 4 on this turn. And then so on and so forth for each one of these possible rolls, right? And remember, our histogram is basically like, of the 27 possible outcomes of rolling this 3-sided die 3 times, 1 out of 27 times we will get a total of 3, 1 out of 27 times we'll get a total of 9, and then so on and so forth. So like 7 out of 27 times, which is actually pretty frequent, we'll get a total of 6 from those 3 dice rolls, right? Now, this could affect player 1's turn or it could affect player 2's turn, but let me write out the code here and we can make it more general in a second. So first of all, let me actually get this histogram back because we want to iterate over these possibilities. And I'm actually just going to make it a constant up here. It is an array of I32s. I don't know if there's a way to get Rust to count this for me, but let's see. It's just going to basically look like this. Let me see. Let me actually just see if I can't just copy this. That is a parenthesis. And we're going to add a parenthesis and some commas there. And a semicolon. It's having a hard time with the underscore. I think I literally need to tell it how many are on the other side. So maybe I can just... Can I do this? It has to know... What if I just shave this off? I think that there are 7 elements here, but like I just want it to tell me. I32, I32, 7, yeah. So semicolon 7. I wish there was a way for Rust to be able to infer that. It's possible there is, I just don't know how to do it. Okay, so now what is it? Oh, it's complaining that I just don't, I'm not returning the right value. Okay, so now we actually have to accumulate what our answer is. So this is just going to be a total here, and it's going to start off at 0, 0, because we don't know, given the starting scenario, how many future universes are there where player 1 wins and how many future universes where player 2 wins, but we can actually calculate it, right? And so for now, let's just consider the player 1 case, okay? So for each of the values in the histogram, so this is the number of steps that you will move forward, and this is the frequency that that number of steps turns up. This is basically the total of the 3 dice rolls, and the frequency is basically the number of times the number of potential universes is that outcome will occur in an iterator over the histogram. And you know, because these are both I32s, I'm going to stick this ampersand in here. This is sort of like a nice little Rust ergonomic thing that I couldn't remember how to do for the last 20 days or so, but I just remembered it. And this will basically automatically dereference the steps and frequency variable here. I mean, really, these can both be U8s. I was using U8s before. Why don't I just do it again? Okay, so what we're going to do here is we're just going to say that, like, the next... Let's just assume it's player 1's turn. So P1 turn, this variable here, let's assume that's true. So let's just let the next P1 position, it is equal to the current position plus the number of steps. And we actually have to wrap this around, right? Because the steps only have values from 1 to 10. So if we remember, the way that we do that is we just want to do it modulo 10. But because the values goes from 1 to 10 rather than 0 to 9, we have to do this like subtraction and then addition before and after the modulo operation. So we're going to subtract 1 here. This will move the space of steps from 1 to 10 down to 0 to 9. Now we're safe to do a modulus, which will give us a wraparound from 9 back to 0. But now that we want the outcome to be from 1 to 10, we can just add that 1 back on after we're done doing the modulus, right? Oh, and let me just return total here so the type checker can stop yelling at me. So now that we know the new position, so in this scenario, the new position for player 1 is just like moving forward that number of steps. We can update the score as well. P1's score. The score is just whatever your previous score was, plus the position that you land on if you take those steps. And now what we can do is we can say that, let's say this is the number of wins for player 1 and the number of wins for player 2 in this scenario. And we just make our recursive call here, right? We're just going to say self.count wins. Oh, I'm not taking self in here. The reason why I need to have a self in this is because I'm going to be caching this, right? This is a method on the solver, so the solver needs some local state. In any other language, I would just make the cache like a static global variable, but that's kind of a bit of a pain in the butt to express in Rust, so I'm just wrapping it in an object, right? And then when we want to actually solve the problem, we'll just like create our object and then call the count wins function on that object. Okay, so we're going to just call count wins recursively, and instead of P1 pause, we actually want to give it a new starting scenario. P1 pause, P1 score, S1 pause, P2 pause, and P2 score. And this last variable is going to change, right? This sort of, I said when I started typing this out, let's just assume it's player 1's turn. Well, the next time we run this function, it's no longer player 1's turn, right? It's now player 2's turn. So we're gonna pass false here. Okay. And the thing with recursion is we just assume this works. The thing to get around your head when you do recursion, and it took me like a year or so of doing recursive problems over and over again to really get this pattern in my head. But basically, we just assume that count wins works. As long as we get our base cases correct, and as long as we get the relationship between this recursive call of count wins and the next call of count wins, then we're kind of guaranteed that it'll work, right? So basically, given this new scenario, player 1 will win this many times with all that quantum unfolding. Player 2 will win this many times. But how many times does this actually happen? How many times is this a future of our current call to count wins? And so the reason why I'm asking that question is because we need to do something with this frequency variable. And what we're going to do is we're going to multiply P1 wins by frequency and P2 wins by frequency and add that to our total for this original scenario that we're in, right? Because remember, this outcome here that I've highlighted on line 46 doesn't just happen once. It actually happens multiple times, right? There are 27 possible outcomes of rolling these dice. And they all happen, right? According to this problem prompt, they all will happen. So what we're going to do now is we're just going to we're going to do total.0. That's just the first element in our tuple. It's going to be P1 wins times our frequency. And the same with P2 wins. Now the type checker is complaining because frequency is a U8 and P1 wins is an I64, but I can just do a cast here, which should be completely safe. I'm just going to cast the frequency from a U8 to an I64. Okay. So this would work in the case that we're passing true as P1 turn, But I mentioned before that we can't actually do that, right? We actually need to have a scenario where we're actually processing this function if it's player 2's turn. Okay, so maybe what we can do in this case is we're probably going to have like if P1 turn do something, otherwise do some other thing, and we could just like copy and paste this code twice in there. That's a bit more repetition than I'm wanting to do, but basically what we need is we need to vary these arguments. And so maybe we can do something like this. Let next P1 pause, next P1 score, next P2 pause, next P2 score. It's basically the word next prepended up in front of all of our argument names, because this is what we're going to pass to the next call. And we've already calculated this for player 1. There's going to be something similar for player 2, only what we're going to do is just rename P1 to P2 in all of these situations, right? It's just going to be totally identical. And then in each of these cases, the next P2 position is just P2 position that got passed in, because if we're in this scenario here, if it's player 1's turn, we haven't changed player 2's position, nor have we changed player 2's score. So those two variables just remain at the same value. And then the next P1 turn, whoops, I should probably rename this here. Next P1 turn. The next P1 turn is just false, right? If it's player 1's turn currently, then the next time we call this, it'll be false. And then we can just paste this in there. This actually didn't end up being less code. It ended up being quite verbose. Here we're gonna swap around P2 and P1. That's P2. Let's move these two lines up. I'm not sure if this is the cleanest way to do it. I haven't really thought about it that much. But next P1 turn in this case, because it's player 2's turn, we're going to go back to player 1's turn. So this is going to be true. And then what we're going to do is just fold these into a tuple. And probably we can just like... actually, I think I need P1 position to be in there. So what I can do is I can just copy this. P1, next P1 score... P2 pause, P2 score, false, right? So it'll look like something like that. So let me just copy this and paste it, and let me be very careful about cutting and pasting here. So all these P1s and these first two lines of this else branch go to P2. This is P2, this is P2, and then let's copy these out. Paste them in, and then this is P1. This is P1, and then finally this Boolean goes to true. Okay, why did I do all that? Well, now I can just update this, and these are all now variables. Actually, I think I saved a little bit of confusion there, hopefully. So what I just did is I said, okay, if it's player 1's turn, here's the stuff we need to pass recursive into the next recursive call. But if it's player 2's turn, here's the stuff we need to pass into the next recursive call. We make the recursive call, we get the number of player 1 wins and player 2 wins, assuming this new starting scenario. We take those values and multiply it by the number of times this scenario will even occur, given that we have 27 different dice rolls in this turn. And then we add that to the total. And this is the structure of our recursive algorithm. I think this is actually a pretty complete description of how the state of this program is going to go. I really wish that the formatter didn't format it this way, but you know what, it's okay. One thing I can do is maybe to save a little bit of save some of these variables is to just do not p1 turn, because we know that it's going to flip. We know that it's going to flip its value, and that way I can just like maybe avoid assigning it here, and this will make it maybe slightly slimmer. Yeah. All right. So now one thing I suspect will happen is that because we're not caching yet, and we knew that we needed to cache even when we were doing like the previous version of this problem, but like the fact that we're not doing any memoization of this recursion means that it's going to run a ton of times, right? Like this position is going to have a value from 1 to 10. The score is going to have any value from 0 to 21. This is going to be 1 to 10. This is going to be 0 to 21. This is going to be true or false. So if you multiply all the possibilities together, you'll get like 10 times 10 is 100 times 20 essentially, which is 2,000 times 20 again, is 40,000, 80,000. Actually, you know, that's not a huge number. But because we're not caching, we're actually going to call the same... all the multiplication that I just did out there is really just the maximum size of the cache. The number of times this will get called with the same arguments is big. And if you don't believe me, you can just like try to write a recursive function that solves like Fibonacci numbers, right? That's sort of the classic day one recursive function. And the difference between memoizing that and not memoizing that is just massive. So since I already have a little bit of infrastructure already to do the caching, let's just go ahead and write our cache, because it's not that hard to add in, right? So the key to the cache is just the arguments that I'm passing into this function. We don't count self here because self is this is just how you do like methods in Rust. We're just gonna have a tuple of U8, 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 and a Boolean. And what we're caching is the result of the function, which is the number of times that player 1 will win in this given this initial condition, and the number of times that player 2 will win given this initial condition. So let's just do an I64. That's our cache. And then what we can do to actually just use the cache is maybe after we've checked these two scenarios, we can just check the cache also, right? So if let some P1 some result is equal to our cache dot get of a tuple containing all of our arguments, P1 pos, P1 score, P2 pos, P2 score, P1 turn. If there's a return value here, we'll just return it. Am I missing an exclamation point or anything like that? Let's cache get. I'm missing the word if. Hilarious. Okay, so this allows us to read from the cache, but we want to write into the cache as soon as we know the result of this, and we do that here, right? We call the function, we get a return value. We might as well just write into the cache right here. One thing that's interesting about that though is maybe we can check the cache down here, because if I check the cache here, what's going to end up happening is that I'll call this function. Let's say these argument values are in the cache already. So we'll call this function, we'll enter the function up here, we'll do these couple of checks, then we'll check the cache, we'll return the value, we're great, but then we're going to write it into the cache again down here. And maybe to avoid that, we can do this check in here. Although in this case, we want to be calling next P1 pos, next P1 score. Yeah, let's just do next in front of everything here. And this is also going to be not P1 turn. Because remember, we're just passing in the arguments that we're going to be we're looking up the a tuple of the arguments that we would pass into count wins. And so if that's the case, we're going to do this. And maybe we can call the result P1 wins, P2 wins. Can I do this ampersand trick that I did before? I can. That's nice. Otherwise, we're going to do this. So I feel like we can potentially make this a little slimmer. I think this is the common piece of code between these two, the two branches of the if-else. So maybe we could do something like if P1 wins, or let P1 wins, P2 wins, equal, we'll fetch from the cache, all that stuff. We're going to do a match on this. Okay. And if we get a result, it's just going to be the result. Otherwise, we are going to do this. Let the result equal this. We're going to return the result eventually, but we also want to write to the cache here, right? So self.cache.insert. And we're going to insert this whole thing. Boy, I really don't want to be repeating that as many times as I am right now. I'll take care of that in a second. So we're going to insert the result. And let's get rid of this. Now that we've got a match, this is actually a little bit cleaner except for the repetition of all these arguments, right? And semicolon. Okay. Is there a way I can bundle these up? Well, I mean, this thing is the same as this thing. So maybe I could say let next args equals, well, I could just do this. This was false. This is true. We'll fetch next args. We will insert next args here. And then the only thing that's remaining is just trying to figure out how to deal with this. So one thing I could do that's a little bit painful, I think maybe the factoring of this kind of needs some help. We could put this into a structure, and that would be a little bit easier to read. Next args.for. Let's see. Oh, and then that shouldn't be there. So this is a little bit slimmer. This is a bit ugly, but I think as long as we've arranged things correctly here, we're okay. Maybe passing these 5 arguments as a structure is a little bit better. But the algorithm is mostly is pretty much the same. So I'm gonna let that be a little bit messy for now. Okay, so then we don't need this line anymore. I don't even know what this was doing in the first place. We actually just need to call this function, count wins, and player 1's position. I'm gonna use the example in here just to make sure I've typed this all in correctly. Player 1's position starts at 0. Their score is 0. Player 2 starts at position 8. Their score is 0. And it is player 1's turn. Oh, and it's a tuple that I'm returning, so I need to debug print it because there's no default stringifier. And this is actually, when I went into this, I was like, I had no idea how to solve this, and it ended up being like a relatively compact problem. Partly I'm not doing any parsing, but I think that I think that like really what we're looking at is not a huge amount of code either way. Where did my terminal go? There we go. Make day 21 be. I don't know how long this is going to take. Wow, that was really quick. Yeah, it's fast. Wow, with that cache, it's really fast. And then if we're looking down here, it says that player 1 wins in some huge number that starts with 444 and ends with 315, and that's what we got here. And player 2 wins with a number that starts with 341 and ends with 808, 808 state, and that is exactly what we've got. So this is really cool. I think we know what I think we basically confirmed that this algorithm works. So we're gonna just say let P1 wins, P2 wins equals this function call. And what we really want to print is the maximum of those two, right? So let's just do P1 wins.max of P2 wins. I'll run that again just to make sure that that code came out correctly. That's great. So let's actually plug in our true input here, which is 8 and 1. Player 1 starts at position 8. Player 2 starts at position 1. And we're going to go ahead and run this. I actually kind of want to know who won. So I'm going to print everything. Kind of didn't need this maximum. I can kind of just read it. So this is cool. In this case, player 2 won, which is interesting, right? Because player 1 actually has a pretty big advantage. Player 1 basically gets to roll first, and because you get to roll first, you're more likely to get to 21 first. So it's actually surprising to me that player 2 ever has an advantage. Let's go ahead and plug this in and see if we got the right answer. Oops, looks like I'm copying and pasting code in here. Let's try that one more time. All right, well, we got it. I'm quite relieved. You know, again, like I felt like my answer for the first part was super complicated, and yet the ultimate problem that we were trying to solve was relatively simple. And I kind of just got stuck thinking about the recursive relationship, which is usually the case for me. Again, like I don't think that recursion comes to me very naturally. But we were able to come up with, I think, a reasonably legible recursive solution here. And it wasn't that bad. I think we just did some simple memoization in this cache, and we were able, even with the debug build, to get something that runs really, really quickly. So that's pretty satisfying. Okay, great. Well, that's it for day 21. I will see everybody tomorrow for day 22.